What is the condition necessary for momentum to be conserved? Well, we said before it has to be a closed system, but how closed does it really need to be? I mean, I think we're going to be able to argue later on that if, say, two cars have a collision, that collision process could be modeled by momentum conservation. Well, how closed a system is that really? It's here on Earth, it's on the road, right? Gravity is affecting it. But maybe there's a way of arguing that it's a closed enough system or an isolated enough system, or maybe even just for a brief period of time, it's an isolated enough system for the momentum to be conserved. So I have this statement that I wrote down when we were looking at the key concepts of momentum conservation can be expressed as change in momentum would always be equal to zero. I think that's a convenient starting point here because we know from the impulse momentum theorem, right, that impulse is equal to a change in momentum. So one way of stating what is the condition necessary for momentum to be conserved is it must be a system that has no impulse applied to it, right? Because if you apply an impulse to a system, you change its momentum. That's, again, the meaning of the impulse momentum theorem. Another way of looking at it, though, is getting into the definition of impulse is force times time is equal to change in momentum. So clearly force also applies a change of momentum to a system. Now, usually in the context of impulse, we were thinking about impulses associated with individual forces, but we've also seen that Newton's second law, talking about the net force, can be stated as saying that the net force is equal to the time rate of change of the momentum. And in fact, these two formulas I just wrote look very related to each other because really if I just divide both sides by delta t, I get one from the other, right? But again, usually for various reasons, we don't write net force here because we like to associate impulse with singular forces, although you don't have to, but that is often how it's done, I guess. But anyways, this statement, though, of Newton's second law, I think makes things really, really clear that if delta P is going to be equal to zero, that is going to be the case only if the net force is equal to zero. Maybe a better way that I could state that is that if the net, let me make that a better E there. If the net force is equal to zero, then that implies that the change in momentum has to also be zero. In other words, that implies momentum conservation. So for any system that I can say that the net force, which really the implication of that is it's the net external force. So at the beginning when I talked about like, well, maybe two cars colliding could exhibit momentum conservation. Well, is the net force on the two cars equal to zero? Well, if we consider the system to be the two cars, we know there's a big set of forces of interaction if the two cars crash into each other, but those are internal forces, so they don't count towards the net force due to external forces, right? Or by Newton's third law, you could argue if you did try to count them, they would cancel out anyways because there'd be equal and opposite forces there. But what about, like, let's say two cars collide and then they stick together and now this wreckage like slides to a halt. Maybe they just hit each other at some weird angle or whatever. As the wreckage is sliding, would the net force still be equal to zero on that, system, the combined system of the two cars? And the answer is no, right? Obviously, I think because the cars are skidding, so the road would obviously be applying a force to them. I mean, if we did a free body diagram, we'd have normal force, gravity force as well there, but while those two might cancel, the kinetic friction force of the road on the wreckage would not cancel against anything, and so there would be a non-zero net force there. But maybe I could argue that just for the brief moment when the two cars crash into each other, maybe just for that brief moment, the net force is zero or close enough to zero that for that part of the process I could apply conservation of momentum. And it turns out I'm mentioning this because that is one of the biggest applications right there. It doesn't necessarily have to be cars. I shouldn't just say we just apply this to cars, but objects crashing into each other, interacting in a very brief period of time, And in some cases, the system might still be interacting with something external, but if it's a brief enough period of time and if the external forces are small enough compared to the kind of internal interaction forces, then you could argue that momentum conservation is correct close enough to get correct results. Anyway, let's look at the answer to this question here. I think it kind of takes the approach of the Newton's second law rather than the impulse approach, and says, so if net force is equal to 0, it implies that the time rate of change of momentum is equal to 0, but 0 time rate of change of momentum implies that the momentum is constant. That's kind of along the lines of what I said, except I kind of made the jump right away to, hey, if delta P over delta T is equal to 0, it probably means delta P is equal to 0. We're kind of not allowing the possibility of delta T. Well, if it's equal to 0, that's problematic, right? But maybe if we're equal to infinity, that's kind of weird. So, yeah, clearly the only explanation is delta P is 0 if the net force is 0. So that becomes the necessary condition. And as I said, meeting that condition is often done by defining a system big enough so that there are multiple objects, and or looking at a process in a small amount of time that we can neglect any forces that might spoil this fact for the interaction that we're interested in.